In this short unit, we're going to take a look at sequences and series. We're going to find out that there's two different types of sequences, two types of series. We'll look at those in the next couple of sections. For right now, though, just as an introduction, we want to think of a sequence a lot like we would think of as a function. And the domain, the inputs for x, is going to be a set of consecutive integers. So I'd like to challenge you real quickly. Go ahead and pause the video, take out a sheet of paper, and I'd like you to add up the numbers, all the consecutive positive integers, starting at 1 and going to 100. So 1 plus 1 is 2, and then you'd add 2 to that, and you'd get 4, and then you'd add 3, and so 4 plus 3 is 7, and then you'd add 4 to that, right? And on like such, until you can come up with a value. And start the video back up when you're done. We'll come back and check in on that little exercise maybe a little bit later on. And so again, thinking about sequences, kind of like a function where we're inserting consecutive positive integers, and if there's not a starting point for our domain, we'll just assume that it's 1. So those values that are input, those are known as the terms of the sequence. And we give those particular names. So the terms of the sequence are known as A sub 1, A sub 2, A sub 3. So when you see that little, it's called a subscript number, when you read it, you say A sub 1, all the way on up till the last item in our sequence, which we don't know what number that is. So we're just going to refer to it as n. And so that term would be the term A sub n. So if we're looking at a finite sequence, it would have a limited number of terms, and so it would come to an end. As an example, 2, 4, 6, 8. An infinite sequence might start 2, 4, 6, 8, and then ... to indicate that it continues on. So if we were to be asked to write down, for instance, a certain number of terms of a sequence, our first job would be to look at the rule. And again, very similar to a function. A sub n equals 2n plus 1. Well, we know that n is going to be our value, our input value, and we're going to start with 1. So A sub 1 would be equal to 2 times 1 plus 1, and so our first term would be 3. Then we would go to the next positive integer, which is 2. 2 times 2 plus 1, so our second term would be 5. So our sequence goes 3, 5, and then we would continue to insert those positive integers. 3, so 2 times 3 plus 1 would be 7. 4, 2 times 4 plus 1 would be 9, and so forth. So our first 6 terms would be 3, 5, 7, 9, 11, and 13. Take a look and just make an estimate before you go any farther as to what happens in example 1b. A sub n equals negative 1 raised to the n power. So now our input is in an exponent. So when we have negative 1 raised to a power, remember, if I have an even number of products that are negative, an even number of factors that are negative, my product is going to be positive. If I have an odd number of factors that are negative, my product is going to be negative. And if I'm multiplying negative 1 times itself, those values are going to toggle between negative 1 and positive 1. So in this case, my sequence would go negative 1, positive 1, negative 1, positive 1, and so forth. So your turn to try a couple. The first 5 terms of each of these 3 sequences. Go ahead and pause the video, come back and check your work. Let's take a look at our first example. So if we're substituting in the values 1, 2, 3, 4, and 5 in place of n, we would have A sub 1 is 1 plus 3 equals 4. A sub 2, 2 plus 3 equals 5. A sub 3, 3 plus 3 equals 6. A sub 4, 4 plus 3 equals 7, and A sub 5, 5 plus 3 equals 8. So the first 5 terms of the sequence would be 4, 5, 6, 7, and 8. So let's check your work on examples 2 and 3. You can take a look at the work there, and you can see that for number 2, your first 5 terms would be 3, 6, 9, 12, and 15. The sequence was 3 times the term number, 3n. And for number 3, now we have 3 raised to the n power, so we're looking for the first 5 powers of 3. 3 to the first, 3 squared, 3 to the third, and so forth. So 3, 9, 27, 81, and 243. So if we can use a rule to write the terms of a sequence, could we go the other way? Could we look at the terms of the sequence and come back to the rule? And yes, as long as we can recognize what the pattern is, it's very possible that we could write a rule for any term. So it's pretty easy probably to skip count 5 or 6 or maybe even 10 terms in, but if we needed the 25th term or the 100th term or the 1000th term, we probably wouldn't want to write all those out. And some very common rules are things like a value repeatedly added to each consecutive term of the sequence, or each term being multiplied by a constant, or each term being raised to a power in the 3 examples that we just saw. So let's take a look at a couple of examples. In example A, we have the term 3, 4, 5, 6. And it's pretty easy to see that in this case we're adding 1 each time. But we didn't start with 1. So if the A value is 1, how did we get from 1 to 3? We added 2. For the second term, it's 4. So our term number is 2. How did we get from 2 to 4? We added 2. So in this case, we have to think about A sub 1 being 1 plus 2, A sub 2 being 2 plus 2, A sub 3 being 3 plus 2. So our next term, we're going to continue to add 2 to the term number. 5 plus 2 makes 7. And so if we needed to write a rule for the nth term, a to the n equals n plus 2. So don't be fooled by the fact that we were adding 1 every time. We're thinking about what happened to the first term to get that value, what happened to the second term to get that value. In example 2b, negative 2, 4, negative 8, and 16. So in term number 1, I multiplied by negative 2. In term number 2, it looks like I multiplied by positive 2. Term number 3, well, what did I multiply by 3 to get 8? So I'm not multiplying by the same number every time. I can see I'm not adding the same number every time. But 2, 4, 8, 16, I recognize those as powers of 2. And in particular, because they toggle negative to positive, I know that it has to be negative 2 raised to a power. So negative 2 to the first is negative 2. Negative 2 squared is 4, and so forth. So our next term would be negative 2 to the 5th power. That's negative 32. And so our rule would be a sub n equals negative 2 to the n. So a chance now for you to try. Let's do a couple of these, one of them at least together, and then you can try the next two with the video paused and come back to check your answers. So if this is a sub 1, a sub 2, a sub 3, a sub 4, if I started with 1, what did I get to 1 to get to 2? 1 plus 1. If I started with 2, what did I do to that to get to 3? 2 plus 1 made 3. 3 plus 1 is 4. And 4 plus 1 is 5. So, what's my next term? To describe the pattern, I'll say add 1 to the term number. To write the next term, well, that's 5 plus 1 is going to be 6. And then write a rule for the nth term. So a sub n equals, well, I can see here's my n value. The n value 1, 2, 3, 4, and 5. So each time I took the n value and added 1. So my rule is a sub n equals n to the 1. Go ahead and pause the video, try these on your own, come back to check your work. So quickly, let's look at our next two examples, 3, 6, 9, and 12. And so it's pretty obvious that we're multiplying, these are multiples of 3, starting with the first multiple, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. So it looks like my rule is to multiply the term number by 3. So the next term is the 5th term, 5 times 3 is 15, and my rule is a sub n equals 3 times n. The next example, a little tougher to recognize. I added 3, and then I added 5, and then I added 7, well, how would I describe that? What did I do to 1 to get 2? Well, I doubled it or added 1. What did I do to 2 to get 5? I doubled it and added 1. What did I do to 3 to get 10? I multiplied it by 3 and added 1. What did I do to 4 to get 17? Well, I multiplied it by 4 and added 1. A little bit later on in math, you'll recognize this type of pattern where first I added 3, then 5, then 7. The second differences are common. Okay, there's a change of 2 every time, so plus 3, plus 5, plus 7. Next one's going to be plus 9, so I know my next term is 26, but how can I write a rule for that? Well, if you recognize what we did, 1 times 1 plus 1, 2 times 2 plus 1, 3 times 3 plus 1, 4 times 4 plus 1. I'm taking the term number and squaring it. So a to the n equals n squared plus 1. Another thing that we can do is we can add up the terms of a series. So a series can be finite or it can be infinite. And when we do that, we add up the terms of a sequence, we get what's called a series. And so we see these finite sequences, 2, 4, 6, 8, and 10, or an infinite series that keeps going and going and going. So in example number 4, we want to take a look at finding the sum of the series. And relatively simple to do. 3 plus 5 is 8, plus 7 is 15, plus 9 is going to give me 24, 3 and 4 and 5 and 6, so 7 and 11. That's 18. So we look at those examples, and adding together 4 numbers, not that big of a challenge. But what if we had a longer series, one with many terms, that really would take too long and would be kind of tedious? So it turns out that there are some formulas for some of the special terms. The obvious one, if I'm just adding 1 over and over and over again, the value is going to be equal to the number of terms. But ones that are a little more uncommon, let's say we started at 1 and wanted to add up the first, say, 5 or 10 or 100 positive integers. 1 plus 2 plus 3 plus 4 and so forth. Well, here's the rule for it. The sum of that series is the last number n times the next number, n plus 1, divided by 2. And there's a similar rule for adding up squares. N times n plus 1 times 2n plus 1 divided by 6. So let's take a look at a couple of examples. If you remember that task from the beginning of the video, here's a little clue on how that might be done and done a little bit more quickly. Maybe we'll come back and look at that. So if we add up 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, it's not that fun, but we definitely could do it. 4 plus 5 is 9, plus 6, that's 15, plus 7, that's 22, plus 8, that's 30, 39, 49, 60. Okay, that's doable. What if we were adding up the sum of the first 100 integers? 1 plus 2 plus 3 plus 4, which is where we left off at the outset. 1 plus 2 makes 3, 3 plus 3 is 6, 6 plus 4 is 10, and you could see that this would take quite a while. But take a minute, take a look at this video, and see how one of math's greatest thinkers thought through this problem. When you're done taking a look at the video, be sure to flip over to the last page and write your summary for the notes. 3 things that you learned today, 2 things that you thought were interesting and you want to know more about, and 1 big question that you still have.